Good afternoon. It's 2:45 p.m. in Philadelphia. Welcome to Thermal Live 2016 again. I'm Graham Kilshaw with Electronics Cooling Magazine, and this is the final presentation in this year's event of Thermal Live. This presentation is selecting the ideal thermal management solution for manufacturing and process technology. Your presenter this afternoon from Wakefield Vet is Mark Polillo, the Director of Engineering for Wakefield Vet, who's located in Raleigh, North Carolina. Good afternoon again, Mark.
Thanks, Graham.
We're also joined by the... Yes, go ahead.
Go ahead, Graham.
I was just going to say a quick hi to MP Divakar, who is the technical editor for Electronics Cooling Magazine. MP is going to join us in the second part of this presentation when we get to the questions from you, the attendees. And speaking of questions, let me give you a few tips on how to use this great platform. There's a Q&A button at the bottom of your screen. Please use that button at any time during Mark's presentation. You can submit your questions while he's presenting. We'll collect them all up. And then Mark, along with MP, will do their very best to answer all of your questions when we get to the end in about 30 minutes from now. There's a couple of other useful tools in this platform that you may wish to take advantage of. You can talk to the other people attending this presentation live now by using the group chat button. If you have any issues with the platform, just go to the yellow tab on your screen and most of the answers are listed there. You can still register, even though this is the last presentation of this year's event, for all of the presentations that have been given yesterday and today, even though they're already done. It's the beauty of digital media. You can register for the recorded versions if you simply go to the Thermal Live website via the link at the bottom of your screen. Look for the link that's shaped like a chain. And the other link at the bottom of your screen, also shaped like a chain, will take you to the Wakefield Vet website for more product information. Last but not least, I already see some questions asking, can you have a copy of the slides? Yes, you can. There's no need to request them. We'll send them to you, every attendee, automatically in 1 to 2 days from now. And a video recording of Mark's presentation will be live on the same link that you used to access today's presentation in about 2 hours from now. And with that, I think we are ready to go. And I'm going to hand over the presentation to Mark. Over to you, Mark.
All right. Thanks, Graham. So just a brief introduction. Wakefield Vet is a thermal solutions provider. We've been in continuous operation since 1952. We have facilities in Pelham, New Hampshire, Raleigh, North Carolina, Withee, Wisconsin, and a couple of facilities abroad. We provide a wide range of thermal solutions to Fortune 50 companies as well as small and medium businesses. And the solutions range from power conversion, telecom, communication, LED lighting, as well as a number of consumer applications. We have a very wide portfolio of products that we produce and sell to customers. So we're always interested in having customers come to us, ask us questions. We will try to steer you towards the most cost-effective solution for what you're looking for. And part of today's presentation, the reason I want to do it, is we get a lot of questions that are, what kind of heatsink do I need, or how do I improve my current solution that I already have? In some of the cases, the customers asking these questions are running into their very first thermal challenge. Some of the customers are non-mechanical engineers trying to play mechanical engineer, and others are savvy engineers who just don't know what to do for their next step. So what I'd like to do as I go through the next few slides is to introduce some basic heatsink construction technologies and also try to explain the when of using technology A over technology B as I go through the various slides. A lot of the information that's here may seem very basic and straightforward, kind of common sense to a lot of us. But again, as we deal with more electrical or non-mechanical engineers that are forced into mechanical engineering roles, they don't know the basics and they struggle quite a bit, and that's a great source of our questions. So as we look at the very first type of heat sink solution, it is a thermal extrusion. It is probably the most common form and easily recognizable that's out there today. It is the lowest cost solution that is available. We start off with a billet of aluminum, a round billet about the size of a telephone pole. We push it through a die, kind of like a gigantic Play-Doh machine, in order to produce the shape. These come in, we can make any shape. We can make any sizes within reasonable limits. We do follow the Aluminum Association for tolerances. So those are much more loose than a machined part. Customers need to take that into account when they try to figure out, how am I going to use extrusion A or extrusion B? You may have to accommodate a slightly wider or longer part than what you're used to, may require secondary operations to make it work. As I said, most of the extrusions we use are aluminum. They are made of 6063, which is extremely easy to push and also has a very high thermal conductivity. When you look at any given shape, you want to look at what is the overall width, what is the height, and also the aspect ratio and fin thickness. The aspect ratio is defined as the fin gap divided by the fin height, and we use that as a way to determine how hard is this shape going to be to push. An aspect ratio less than 7 is very straightforward. Generally, those push without too many problems unless you run into thin material. Less than 10 may require us to slow the process down so that we can reduce any damage to the tool that we may have. Shapes that are greater than 10 require a lot more care in terms of both the tool design and its operation to make sure that we give you a good product. Now, typically, these aspect ratios are good for extrusions that are less than 8 inches in width. Wider extrusions play by a different set of rules, and those usually need to be evaluated on a case-by-case basis. Most customers are using extrusions for board-level devices like TO220s, all the way up through high-power devices like IGBTs and power amplifiers. And again, whether you can use an extrusion or some of the other technologies here depend on a lot on your environmental conditions that you have. Do I have enough airflow? Do I have enough surface area? And those are going to hold true for all types of technology. So the goal here is to just educate you on the type of technologies that are out there, and then we can evaluate their overall performance. So what happens if you run into a situation where you need a solution that is wider than what can be pushed as an extrusion today? In this case, what we do is we try to push customers towards a bonded fin heatsink. We start with an aluminum plate that either is extruded with shallow grooves in it, much easier to push than a full size, or we can do the grooves. The fins are bonded. They're using thermally loaded, but they can also be done with a brazing weight as well. Brazing would give you the best performance, but there are some drawbacks with regards to those and also your material placement. One of the other common things that you do with bonded fins in order to make them is to actually create what we call sandwich-style bonded fins, based on the bottom, based on the top, and a fin stack. Typically, this allows customers to have smaller footprint because it's not devices on both the top and the bottom, and either have natural convection or forced airflow through the metal. Also, because the base and the fins are such a pieces, you can mix them back and forth. So you can fin, copper base and aluminum fin. Usually you can do this for thermal conductivity or for weight reason. And a couple of the heat sinks that we've produced in the past for extreme weight solutions actually use graphite fins, which are actually lighter than aluminum, but have a thermal conductivity equal to or better than copper.
Hey, Mark, it's Graham. I'm sorry to interrupt the presentation. We seem to be having a little bit of difficulty with the audio on this. Can you hear me, Mark?
Yes, I can. Can you hear me now?
I can hear you clear now, but your audio suddenly went very low quality.
Very quiet?
It seems to be better now. Did you? And my apologies to the audience for the interruption. We want to try to make sure everybody can hear what Mark's saying. Did you make any changes, Mark, while you were presenting there?
I did not.
No,
but I'll keep an eye on it in the future.
Okay. Why don't we go back just to maybe to the beginning of slide 4, Mark. We lost you at about 2 minutes ago. Not lost you completely, but the audio went bad. I suggest we go back to slide. Sorry, you're on 4. Back to slide 3. My mistake. And start again there. And attendees, if you're still having problems, please put a message in the box. Somebody actually just requested, can we start from the second slide, Mark? I think that's where we lost the quality of the audio. If you have problems, attendees, please put a note in the box. We will be monitoring it. Okay, let's carry on.
Okay, so slide 2 was just the introductory slide. Slide 3 is where I was talking about thermal extrusion. Let me get back to my slide. Okay, so aluminum extrusions are the most common form of heat sink that's out there. Typically, we use 6063 aluminum, which is easy to push through a die. It has a high thermal conductivity. In the way an extrusion is made, you start off with a large billet or log of material. It's about the size of a telephone pole. And you push it through a die kind of like an old Play-Doh machine. Your shape comes out the other side. And then there are secondary processes that are done to it before you can actually use just the raw material. And that includes cutting out the sections where we join the billets together, as well as tempering the material so that it is hard enough for us to machine and drill and tap holes into. As we look at extrusions, one of the ways that we try to measure the difficulty of, can this extrusion be made, is we look at the overall width, the height, the aspect ratio, and the fin thickness. The aspect ratio is defined as the fin gap divided by the fin height. And what we're trying to look at here is, if we have an extrusion that is a 7-to-1, that's typically extremely easy to do. Less than 10, we may be required to run the tool a lot slower so that we don't do any damage to it. Greater than 10 means that we have to take a close look at how the tool is produced. We have to take a look at the shape to make sure that it is suitable for manufacturing and that we're going to get a good quality product out. These aspect ratios apply for extrusions that are typically less than 8 inches in width. As you go above 8 inches, the rules change, and those need to be evaluated on a case-by-case basis. As you look at extrusions, customers are using these for board-level devices from TO220s all the way up to high-power products. And whether or not an extrusion will work depends on your thermal boundary conditions. Do you have airflow? Is it natural convection, forced convection? Do you have enough airflow? Is your heat sink large enough? Those types of questions are going to apply regardless of the technology that you're using. And it's something to keep in mind in the background. These are the questions that our application engineers help customers with every day when they call in and ask their various questions. So what do I do if I have an extrusion that is too wide or too tall to be produced? And so we have an alternative technology, which is a bonded fin. We typically start with an extruded or machined aluminum base that has a series of shallow grooves. Into the grooves, we're going to install individual fins. The fins are a stamped out piece. They can be any height, any shape, so long as we have a nice flat edge to be able to join them into the base. Fins are typically 32 thousandths of an inch or thicker. Thin fins are much harder to deal with, and there are other product styles that lend themselves very well to much thinner fins. In most cases, customers are using a bonded fin, have a single base, and then one set of fins. But we've seen a lot of interest in customers trying to reduce their overall footprint by using what we call a sandwich-style bonded fin, which is a base, a fin set, and then another base on the top of it. This allows customers to put devices on both the top and the bottom and end up with a smaller product than what you could if you had a singular device. Because the base and the fins are separate pieces, you can actually mix and match metals. So we do aluminum fins and aluminum bases, but we also do copper fins, copper base, mixed with aluminum fins and aluminum bases. A lot of that depends on what is your weight, what is your thermal target. If weight is a huge constraint for you, we've actually done designs that are based on graphite fins, which have a thermal conductivity equal to or better than copper, but at the same time are about as light as aluminum. Another alternative when you're looking specifically at a sandwich-style bonded fin is what we call our stacked fin product. Here what we do is we extrude an I-beam. And the base and at the tip, you have an interlocking set of grooves. The parts are stacked together. The part is compressed so that the interlocking grooves lock with the mating features. And now you have a singular heat sink stack that can be machined. You can put holes in it. You can do all sorts of other things to it. It's a little bit more stable than a bonded fin. You don't have the advantage of now mixing copper and aluminum together, but a lot of customers find that this works very well for their application. One downside is because each fin is extruded and has its own tolerance, the tolerance on the overall width of the part is cumulative. So if you want a 9-inch extrusion and 15 fins, you might actually end up with a 9-inch wide extrusion that has 14 fins if all of the fins come in slightly oversized. But what if I want really thin fins? We see a lot of cases where customers are looking to put multiple heat sinks in a straight line. The thicker fins of a bonded fin, a stacked fin, or an extrusion are just too wide to provide adequate cooling for the last device in the row. So if you had a way of pushing an extrusion with 5 or 10,000 stick fins, you could actually have a thermal solution that works for the last device, but that's outside the realm of extrudability. So what we introduce is a folded fin solution. The fins can be made out of aluminum, copper, stainless steel as common materials. Looks like the interior of a piece of corrugated cardboard. It is a continuous sheet of metal that is stamped and folded into the required shape. Fins generally range from 2/1000 up to 80 thousandths of an inch. Most customers use 10 to 15 thousandths. So they're getting something that is significantly thinner than what you can extrude. Just like an extrusion, there is a limit to the aspect ratio on these. As the height of the fins get taller and taller, the tooling requires the fins to get further and further apart. This can be overcome with some alternatives that I'll show in a couple of minutes. Like a bonded fin, the fins are separate pieces from the base. They need to be attached either with a solder, an epoxy, or a brazing operation. One of the downsides of a folded fin is because of the thickness of the fin, they're extremely hard to machine after the fact. So if you want holes or cutouts or other features, that can be problematic. Typically, those are wire EDM'd into the part before it's actually bonded to the assembly. Some customers actually prefer to use just smaller sections of fins and just gang them up on a part rather than go through the expense of wire EDMing out the individual profile. One other advantage of folded fin is that in addition to being able to be used in air cooling, they can also be used in liquid cooling, where you can actually put them in the fluid channel and provide a localized area of extended surface area in order to improve the thermal performance. Now, in the folded fin, you have thin fins, but you have that bonding agent. A lot of customers get concerned over the fact that they don't want that extra layer of interface between the fins and the base. So if you still need the thin fins, you can live with some restrictions in terms of height. One of the solutions that's out there is a skived fin. We start with a block of aluminum or copper. There is a tool that comes across the top of the part, and it raises the fin. It basically slices down into the base and raises up a small burr. The fins typically are between 0.5 and 0.7 millimeters thick, and you have a height of 50 millimeters or about 2 millimeters, or 2 inches in height as a limitation. If you want a taller heat sink, that can be done, but typically the fins end up being closer to 2 or 3 millimeters thick, but you do end up with that solid base at the bottom. The base thickness for a skived fin, due to the stress that the tool puts on the part, has to be at least 4 millimeters in thickness. We can machine it down afterwards, but if you want to try and avoid secondary operations to make the product as cheap as possible, aiming at a 4 millimeter base will give you the best success. One point of note is that because of the way the fins are formed, one side of the fin is going to be extremely smooth. The opposite side of the fin is going to be extremely rough. This can be problematic when people start looking at how much pressure drop there is, or if they're worried about a high dust environment. It's very easy for the system to actually act as a dust collector if there's not a filter someplace in the system. Because of the thickness of the fins and the way they're formed, they are a little fragile. So we do recommend that customers put a shroud over the tips of the fins just to provide them some level of protection, either shock and vibration or even just during basic transit. But what if I want really thin fins? I want a high aspect ratio extrusion or a high aspect ratio solution, something that exceeds either folded fin or skived fin. In this case, we introduce a zipper fin. Each fin is individually stamped out, typically made out of 10 thousandths thick aluminum and or copper. The fins have an interlocking feature that ties the first fin to the second fin. These features are automatically joined together in the tooling so that when you pop this part off of the tool, it is its own fin stack. It is something easy to handle. If you want to mix and match material, you want to mix and match different lengths or heights, then the zipper feature are put in specific locations such that they can be manually joined together in order to provide an overall solution. The fins can be stamped such that they have open tops or where they have closed tops. A closed top solution is going to capture the airflow, so as it's blown through the heatsink, it's not allowed to escape out the tops of the fins. Thereby, you can have better use out of it or direct it to a secondary heatsink that is downstream in the case of multiple solutions in a row. The fins are typically bonded to a base using either epoxy or solder. One advantage of the zipper fins is they are stamped, so you can incorporate extra features in them like dimples for extra surface area, You can put in notches to provide clearance for other devices, or you can incorporate features to allow the use of a heat pipe. That way there you can, in the example that's shown there, the heat pipes are U-shaped. They come out of the base, curve up in the air, and connect to the top of the fins. It allows you to drive heat both into the base as well as into the tops of the fins to provide a more efficient thermal solution. So all the solutions I've talked to now are, you want a high density in order to get your thermal performance. But what if you run into a situation where I want a complex shape that doesn't necessarily need a lot of fins? You may be looking to combine the chassis and the heat sink together. In this case, we recommend a die cast solution. There are lots of different die casting or casting processes. You can have investment casts, permanent molds, the most common of which is a high pressure die casting. Each one of the processes has limitations with regards to minimum feature size or tooling cost, and also the longevity of the tool. Investment castings are great for maybe less than 3,000 or 4,000 pieces, whereas permanent mold can do 50,000 and above, but you wouldn't necessarily want to use it for only 1,000 pieces. Downside of a die casting is that the material is porous because of the way it is formed. This can impact the thermal performance. What we've seen is based on the alloy that's chosen, you can have thermal conductivities between 80 and 170 watts per meter K compared to an aluminum extrusion at 200 watts per meter K. Castings also allow you to use different materials. You can use a zinc, a magnesium, or a copper, and you would go with a copper if you're not concerned with weight, but you need the high thermal conductivity. Zinc or magnesium will still work for a thermal solution, but they're also going to be extremely lightweight. So I've mentioned a couple of times in the presentation using heat pipes to enhance the capability of any of these technologies. But what is a heat pipe? So it's a tube with an internal wick structure that has a small amount of fluid. Now, they're called heat pipes, but they actually don't help you get rid of heat. They are simply a transport mechanism. They will pick up the heat from point A, move it to point B, and provided you have met the correct thermal conditions at both A and B, the pipe will continue to work. If you are not able to provide adequate to get to point B, you may not be able to have the internals function. Inside the part, there is a wick structure with a fluid. It is most commonly water, but you can also use ammonia or alcohol, and that will depend on what your operating conditions need to be. Most consumer applications are going to be able to use a water-based pipe. The water inside the part will boil once it reaches a given temperature. It will travel down the interior of the pipe in vapor space. When it gets to the opposite end where the fins are, or to a colder point on the heatsink, the vapor will condense and turn back into a liquid, and therefore it will be pumped right back to the hot end of the part again, and the process continues to repeat. We have a variety of these in standard lengths and diameters that we offer through our distribution partners like DigiKey. If you're interested in taking a look at these or want to experiment further. But now, what do I do if I can't get there with traditional air cooling? Either your device has extremely high power in a very small area, or you have too large of a heatsink that you're trying to deal with. And this is where most customers transition from air cooling into liquid cooling. Liquid cooling, the examples that are shown on the page here all use tubes, but there are other construction methods, which I'll show in a chart in a moment. Typically, you're going to pump a glycol water through the system, although there are customers that are both using liquid refrigerant as well as two-phase refrigerants to try and achieve higher level performance. A cold plate requires that you have a pump and then a condensing section. So it is a little bit more technically challenged to deal with than just an air-cooled heatsink, because you have to have knowledge of your pump. You have to make sure that you've picked a radiator and a fan combination that is able to pick up your rejected heat from your cold plate and reject it out into the airstream. You undersize the radiator, or perhaps you oversize the pump, you may not be able to achieve the necessary thermal balance that you're looking for. So this is a chart of traditional cold plates that are out there in the industry today. There are a lot of different construction methods that are out there today. The first four that are on the list are based on a tube. We offer standards through our distribution partners for the first three that are on the list, a rolled tube, a full buried where the tube sits completely below the surface of the part, or an exposed tube where it sits right on the top surface of the part. Half buried is another tube-based solution, typically done on a case-by-case basis that the engineers will represent once we've reviewed your product. Brazed, gaskets, and welded solutions are all examples of having internal flow passages. It allows for a much more complex cold plate. Instead of having a single tube that runs in a pattern on the plate, you can bring the fluid in, you can split it, run it in different directions, you can move it from the top to the bottom of the plate. There's an unlimited number of combinations that you can do, and that can be evaluated by the applications engineer. Brazed and gasketed and welded would be where you could introduce your folded fin, such that you could get higher heat transfer in just localized areas to get rid of the heat from that one problem device that you're trying to deal with. So this outlines the various technologies that are out there. There are more advanced solutions that are there. There are ways to combine these solutions. You can have a cold plate with fins on it, where you're taking advantage of both liquid solutions as well as air-cooled. But this is trying to explain the basics out there to mechanicals who may not know what their next step is, or for the electrical engineer who's been forced into a mechanical role, who has no idea how to deal with the thermal solutions that they're having to come up with. And so now I'll turn it back over to Graham and MP for any of the questions we may have.
Hey, thanks, Mark. Very interesting presentation, and certainly a useful one, as these technologies are very widely used in the electronics design field. I see we have several questions coming in, and so I'm going to pass them right over to our technical editor, MP Divakar, to begin this portion of the session, and MP is going to field the audience questions. MP, over to you.
Oh yeah, thank you, Graham and Mark. Very nice presentation. I enjoyed it. I have a few from my side. I'm going to keep them short and then yield to the audience question. Regarding outdoor applications of heat sinks, what is the, for aesthetic reasons, people have them painted. What is the best choice there? Is that powder coating a better solution, or is there any UV resistant paint, or what do you recommend for heat sinks outdoors?
So typically for outdoor applications, if there's an environment where you're going to be in, say, a marine environment or subject to salt spray, we recommend a basic chromate application. There are a number of different specific chromating steps that you can do that'll give you a high corrosion resistance to the surface, so that you're not oxidizing either the aluminum or the copper. If it's a cosmetic application, you can do a paint or you can do a powder coat. challenges sometimes on the paint, if you have a very high aspect ratio extrusion, will be to be able to spray that paint all the way down to the very bottom of the fins, especially if they're very close together, in which case most customers will shift over to a powder coating type of application.
Okay.
For all of these solutions, the coating is it is a barrier to the thermal performance, and what most customers should do, they don't, but a lot of customers should do, is where their devices are mounted, actually remove the paint or the powder coating. It's okay to leave the chromate, but that extra layer of paint or that extra layer of powder coat, if you're trying to mount your device on it, can be a huge thermal resistance and can cause a lot of problems downstream.
Okay, yeah, that's a good point. Let's go to the audience question. Jose has a question on the impact of having fins glued instead of being monolithic. Can you quantify this for thermal resistance?
So when you make a bonded fin or you use, say, a folded fin or a zipper fin, the goal here is to minimize the bond line. We typically aim for between 5 and 7 thousandths of an inch when we're doing epoxies. Or solder or brazing, that typically actually moves down to about 2 or 3 thousandths. So when you look at it from that perspective, the thermal epoxy is loaded. It does have some alumina or some copper particles in it. It has a higher thermal conductivity than, say, a super glue. They typically range anywhere from 4 to 10 watts per meter Kelvin, which for an epoxy is extremely good, but when you consider aluminum is 200, it's not really that great. The impact is hard to quantify unless you know how much airflow do you have. If you're in a very high airflow environment, then the thermal epoxy can be a huge impedance to you, or it could be extremely small. It depends on how your system is set up.
Okay. Russell has a question on the folded fins. How are they bent into shapes? Probably a tooling or fabrication focused question.
It is. It's actually a fascinating process to watch. There's a couple of different methodologies that are out there. Some customers will feed the material through a set of gears. So your gear tooth will fold the material up while the next tooth is folding the material down. That typically would give you the style of fin that you would see in a car radiator. For the folded fin that I showed in the example, it's an opposing set of tooling. They're not really square corners. Some of them can be rounded, and there are obviously different configurations. The two tools collapse onto the piece of material, bending it into shape. As the jaws open, the material moves back. Usually they capture one last fin of it to keep the spacing correct, and the tools close again. It's just a step and repeat. They'll run strips and strips of material through the die at the same time.
Okay. We are filling up with questions, so I'm going to do some random selection to cover as many broader topics as possible. Marstaba has a question on using different metals in heat sinks. Won't there be a risk of galvanic corrosion if you use different metals?
So we see galvanic corrosion more in liquid cooling applications where the water is carrying the potential from, say, steel into the aluminum or steel into the copper. We don't recommend mixing steel and copper. We always recommend the use of stainless steel. But when you do have to use it, there are ways to mitigate that by using water or a fluid that has an anti-corrosion additive to it. It impacts the thermal performance a little bit, but it'll solve a lot of headaches in the background.
Okay. John has a question on the application of graphite. What is restricting
Sure.
or preventing graphite as a common material for heat sinks?
Most of it is the cost. Graphite fins are extremely expensive. Graphite itself is expensive. It is hard to machine and keep it in shape. When we do the graphite fins, we actually cut them with an X-Acto knife, score it, and break it. And occasionally it will break not where you scored it, but a little bit further over. And so that causes problems. So when you try to look at using that same material as a entire heat sink, you have a lot of issues.
Okay. E. Zhang has a question on enhancing the radiation from heat sink. What can you do in terms of surface treatment?
The most common treatment is to anodize the heat sink. So that will work for an extrusion. You can anodize a bonded fin, but what you would have to do is anodize the fins first, then anodize the base, and then put the two together. The thermal epoxy that forms that joint does not do well in the anodized process, and so that is an issue. If it's a brazed solution, if you had folded fin or bonded fin that's brazed, after the brazing operation, that is an aluminum-filled material, so you can put it right into the anodized process, and that will help. That's the number one thing that most customers will do to improve the radiation.
Okay, yeah, that's a pretty good suggestion. Bonnie has a question on the solder joint. How do you ensure the quality of solder joint in zipper fin heat sinks?
So, a complicated question. When you sit down and you start looking at what the base looks like and what the fin looks like, we've gone through a lot of experimentation and a lot of validation of how do I lay down my solder paste. Do I just lay down one big square? Do I put it down in a pattern? How much is too much? How thick do I put it down? There's obviously a lot of variables.
Okay.
What we've done is run through some various experiments and then actually done pull testing. You'll hold on to the base, grab onto the set of fins, and pull up on them either straight up or actually just trying to peel them off of the base to see, how much force it takes to break these. In some cases, we've ended up with joints that are strong enough that we've actually ripped the material before we have separated the fins from the base itself.
Okay. Those, would you say, are generally adequate? And if you pass those, most likely the joint will survive, when subjected to a shock environment.
Correct. And a lot of we've had a lot of customers that have done their own shock and vibration testing on these. I can't think of too many of them that have ever failed.
Okay. Jacob has a question. What are the design rules in selecting the fin thickness?
So on an extrusion, if the minimum fin thickness is 25 thousandths, and that works well for short extrusion, say less than an inch in height and up to, let's say, through 2.5 to 3 inches in width. As you start to go a little bit wider or as you start to go taller, your fins start to increase. And some customers will now want to introduce also a tapered fin. So it's thicker at the base and thinner at the tip. That helps with the tool strength. All of the rules that I outlined with regards to the aspect ratio are all to make sure that the steel tool that we push the aluminum through has a long life and doesn't break. If you think about the tool being the reverse of the extrusion, a very narrow gap between fins that's very tall leads you to have a piece of steel that's very thin and very tall, and that's easily broken. So sometimes just adding a little bit of taper to it can help quite a bit. Other cases, you just have no choice but to eliminate a couple of fins and try to look at what that does from a thermal performance aspect.
Okay. A somewhat relating question, and that is by Eduardo. He's wondering if there is any software or application that he can use to specify a heat sink that he can build for his application.
If you're doing high-end design, yeah, it is. Yeah. If you're doing high-end thermal design, you can use tools like ANSYS's IcePack or Flowtherm to perform analysis. There are a number of websites out there that have some basic tools that may allow you to analyze the number of fins on a heat sink and how that impacts the performance. But in most cases, those don't take into account the design rules. They'll just simply say, this is the best heat sink you can have.
Right.
Internally, we use both our IcePack tool as well as some proprietary tools to help look at optimization of the heatsink and to make sure that it is actually producible.
Okay. Just another point, to Eduardo, check back on our website, electronics-cooling.com. There's plenty of resources for heat sinks and heat sink selection criteria, things like that. Let's get to the last question, again from Mashtaba, and he's got a question on the fin height and fin thickness and their limits to manufacturing, basically an aspect ratio question. And what he's wanting to know is, what are these aspect ratios, especially if you're using extrusion, to fin thickness, limits thereof?
Right. So in most cases, we kind of discount what the fin thickness is when we're looking at aspect ratio. It's more a function of the gap and the height of the fin, because that's what actually defines the strength of the tool itself. Now, having said that, you jump over to, are there any secondary operations that are going to be done? A lot of customers will take an extrusion and they will cut the fins 90 degrees, creating a cross-cut heatsink, because they may have airflow that's coming in at an odd angle, or they may be trying to use one heatsink in multiple applications where they have flow from different directions.
Okay. I think
now you have to look at the manufacturability of the crosscut. Now the fin thickness actually does come into play.
Yeah. Thank you. Thank you for the answers. I think we've come to the end of the presentation. I'll keep another few seconds on the Q&A panel. I don't see any. In closing, I think we've had a great presentation and lots of useful information. I enjoyed it, got some very practical, usable, and value-added tips from you, and thank you for taking the time to present. And let me hand off back to Graham for the closing comment or closing summary of what's been a great 2 days of Thermal Live. Over to you, Graham.
Thanks, MP, and thanks, Mark, again. Yeah, great presentation. I'm sure everybody enjoyed it, and judging by the number of the questions, the attendees got a lot out of that. I just wanted to say, as we come to the close of the 2016 edition of the Thermal Live event, to thank all of the attendees this year. If you were interested to know, there were 2,806 registrations for this year's event. It's only our second year, but clearly it's gaining in popularity. So thank you all for registering. I have a little bit of information coming up in a few minutes about next year's event. Before that, though, I want to thank all of our presenters. And if I can pull up them on my phone, I want to quickly mention them. They were tremendously strong presentations this year. And I want to say thank you to ANSYS and to Autodesk and to Celsia, Henkel, Mentor Graphics, also to UiCode, DuraTouch this morning. Their presentation on wearables was very, very interesting. Avid Thermaloy this afternoon, followed by Phononic, Six Sigma ET, which is part of Future Facilities. Finally, Mark and his team at Wakefield Vet. But a great group of companies. We thank them for their support and sponsorship of the event. And we hope that all of you will get ready to sign up for next year. We'd also like to see some new companies presenting next year. We're always looking for the innovations and technologies that are emerging in thermal management. And so next year, the dates have been set. If you want to make a quick note of these for your calendars, October 24th and 25th, that's a Tuesday and a Wednesday, 2017. We look forward to seeing you all again then. And, of course, you can continue to keep up on your thermal management education and learning by following the Electronics Cooling newsletter each week. Thank you to everybody. We hope you had a great couple of days. Bye for this year.
Thank you. Bye.